Well, you know, it's an MP3 player slash camera that was also a telephone, or is also a telephone. Web browser, et
Yep.
cetera, et cetera. There was a once upon a time my kids had MP3 players and smartphones. They thought they
Yes,
needed
I saw
both.
that. I saw that with high school kids in the 90s and early 2000s
And I think the reason for that was is that you could put a lot more songs on a
on the MP3.
on an MP3 player, but nowadays you just subscribe. You're paying $10 a month or whatever, $9 a month,
Yeah.
and you're listening to millions of songs. That you
Yeah.
don't have to
I
put on your phone.
my 2017 automobile has a CD player and a connection for an MP3,
Mm-hmm.
but it also has satellite radio. So I
Right.
do satellite radio and I don't do either of the other things. I don't think my CD player has ever been used.
I've never used wine.
I see that argument going on with people with film collectors, because almost no one has a CD library anymore.
Nope.
And the guy who wrote the article about the iPod was saying, the iPod really killed both the necessity for and romance of having a CD library. Here's my collection of music. And much the same way, people are saying, "Oh, well, I don't collect movies. I buy a streaming service." But the problem I've seen with streaming services, being a fan of genre films like film noir and silent film and classic detective fiction, is that you can get the newer stuff on streaming service, but the older stuff, even when it was there for a time, they've taken it down.
Yeah.
And I'm like, you know what? If I don't own the media, I don't own the right to see my favorite films whenever I want. And so all I can do is hope my streaming service will allow me to see my favorite stuff.
Yeah.
Sorry,
That's
I'm not
true.
buying that.
That's true.
So I have this very large film library, 4,800 titles. And I just spent a substantial amount of money to upgrade my shelving because I have a stupid amount of, I have now five 7 foot tall, 3 foot wide shelving units to
Mm-hmm.
hold my films. And I have room to grow now, where before I was stacking things and wedging them in and stuff like that. So,
Right.
and I'm sure if you're an aficionado of, things like classical music, and you like certain performances by certain uh, conductors,
Yeah.
you have to have physical media because you just can't get that on streaming.
Right. Well, and even beyond that, the quality of a compressed streaming,
Yes.
you know, performance is, if you're an audiophile, that's really not quite good enough.
No, it's not. It really is not.
So, and if you're a movie aficionado and you have such greats like Citizen Kane and some masterpieces of cinema that you really love, for whatever reason, you want to have as high res as pure sound, visual, everything,
Yes.
for your private theater.
Yes. Yes. And I'm a big fan of classic films. So
Yeah.
almost no comedy in my collection.
Oh, really?
Yeah. I just don't do that.
Don't do comedy, huh?
No.
So Airplane is not part of your classic collection?
It is not. I have some comedies that date from 1950 and earlier.
Okay.
I have some what you would consider romantic comedies, but mostly before 1970. I have some comedic films some people have given me. But a lot of modern comedy leaves me absolutely flat. Like I say, we went to see Fiddler on the Roof. I really didn't like it. We got very nice seats at the Walton Arts Center and all of that. And I've never seen it. I remember when it came out in '73 with Topol and all of this. And I'd never been particularly interested in it, never seen a review or anything. I had heard some of the songs because it was such a big deal when it was on Broadway and then as a musical. And at that time, very popular films, and you would hear songs from movies on the radio. So I'd heard If I Was a Rich Man and some of the other things. And my wife said, "Ooh, it's coming to Fayetteville. Let's get tickets." And this was some months ago. She said, "Would you like to go?" And I said, "Sure, fine." And it went beyond tragic. It was kind of a disaster movie with songs.
Oh.
And I said, I was really looking forward to this, but I really didn't like it.
Well, I think we're ready to get going here.
Anytime you are.
Okay.
Three, two, one, fire.
If there is a question that we don't know the answer to, we will test it.
Sequencer on. 5, 4,
3, 2.
1.
I know what that is.
Now that
Hey,
the
Mars
Perseverance rover
sample
has started
return.
to collect the first samples, that has kicked off the Mars sample return mission.
The goal of Mars sample return is to pick up those samples from Mars and bring them back to Earth.
This mission has many crucial components involving many NASA centers as well as international partners. The tests we're running right now are just the first step in making this mission possible.
What this testbed is working to achieve is early prototype drop tests for the sample retrieval lander that's going to go pick up the rock samples on Mars. 3, 2, 1.
After we've landed on Mars, the samples have been transferred into the Mars Ascent System.
We take the rocket and we actually throw it up in the air before we light it off.
It's an ambitious effort because we had never done this before.
Sequencer armed. 3, 2, 1, fire.
This test that we just did goes a long way to showing that it's possible.
That this is the correct path to go down to have a successful launch on Mars.
Once the samples have left the surface of Mars, they will be captured by the Earth Return Orbiter, where they will be safely contained so they can be brought back to Earth.
This particular tower is designed to test out one of the last elements of Mars sample return, this impact landing on Earth.
3, 2, 1.
We get to demonstrate how strong these hardware elements are to prove that these samples can be brought back safely, that we design a system that can stay contained and keep these Mars materials separate from the Earth's biosphere. We're still in the development phase right now, and so we're still using these tests as a learning mechanism.
We need to know the information to make sure that we can make a mission on another planet work.
In order to accomplish goals such as bringing samples back from Mars, you have to sometimes dare mighty things.
Wow. I just saw that they tested the sample return, dropped it from a helicopter, 1,200 feet.
1,200 feet, huh?
Somewhere into the desert. And I'm like, wow, bang.
Right.
And
Yep.
that's just spectacular engineering, Scott. It's just spectacular. So I'm so looking forward to seeing when those samples get back and the OSIRIS-REx samples get back. Not that I'm going to get my mitts on them, but the data will be here and I can get my hands on that. So that's really exciting stuff.
Awesome. Awesome. So your program today is about, it's called Mars Inside and Out. It is
Yes.
about the chemistry that's on Mars, the interior makeup
Yes.
of Mars,
Yes.
the atmosphere, water, everything, kind of a holistic view of
A
what
holistic
Mars
view
is all
of
about.
it all. And you know, I do kind of opening comments things. And I saw, oh, there's all these little bit pieces from Mars in the last couple of weeks. And I'm like, ooh, shiny. And I just realized, you know, I can have a whole show on this. And I love Mars. I've been a fan of Martian exploration since well before Viking. I'm talking Martian Chronicles as a kid. Golly, all that stuff. And I just, as I often do, I start out looking for the shinier pebble on the beach. And I want to see the next shiny thing. And I go, wow, you know, I hope that when I look at this stuff and I go, gosh, that's fascinating. I love this. I think what we've found together as an audience in the last year and a half is that, yeah, stuff that delights the old guy, delights a lot of people around the world in our audience. And that's why we're still here after, you know, 46 shows, which I'm very excited about. Very excited about. So we've got some good stuff today.
Absolutely. Well, I'll let you get started here.
Okay,
Thanks.
well, welcome everybody to episode 46 of How Do You Know? And very glad everybody is here. We're looking forward, coming up to episode 50. We still have hope, cross fingers, knock wood, that indeed the book, the next book, Star Mentor, will be out physically in our hands because we're planning a giveaway for episode 50. And if the books aren't in our hands, we'll have the giveaway show anyway and get them to you as soon as we have them available. But we're looking forward to that. We'll let you, the winners, tell us what they would like written in their signed copy, and we'll get more details to come. So as we often do, let's start the show with some show notes, some interesting things that's shown up in the news. I've had people say, well, what's on your phone? And you probably know that all of the information services, whatever we're talking, mainstream media, we're talking social media, we're talking search engines, they all look at the stuff you look up and they sort of, you know, they show you, ooh, this is fascinating for Doc. Let's show him more of this stuff. Somebody said one time, one of my students said, well, what kind of junk do you have on your phone? I said, well, here, have a look. And they looked at the search engine and they go, my God, it's all cars and rockets. I'm like, yes. Yes. Fast cars and rockets. So let's talk about some of the fun news. Today, talking 50 years after Apollo 17 in 1972. And I saw a video of Gene Cernan's speech as he was climbing up the ladder. And he's talking about, as I put the last footprint on the moon, we came here in peace for all of humanity as explorers, and I'm excited because we will soon be back. No.
Well, if you take the human timeline.
Oh, yeah, if you're talking the invention of
take
fire.
the human timeline to the point of the dawn of humanity to the point where we put boots on the moon.
Yes.
To come back in only 50 years
okay.
is like a blink of an eye, right?
Yes, true. And
He was probably thinking of a shorter timeline than that.
yes, I was. For me, there are two examples of timelines of space exploration. It's 1961 and Rice University, and Jack Kennedy says, "We choose to go to the moon and do the other things in this decade, not because they are easy, but because they are hard." And I was so, I was a little tiny baby when that came out, but they played that over and over again after Kennedy
we've been hearing
died.
it all of our lives, and it's still inspiring when you hear it.
And it just sets me on fire.
It doesn't sound dated.
From 1961 to 1969, 8.5 years, and we didn't have anything. We didn't have any of the technology. We didn't have the rockets, the spacesuits, the life support systems, the telemetry. We didn't have the guidance systems. We didn't have the lander. We didn't have the command module. We had nothing. And 8.5 years later, bang, there we are. And everybody said, it can't be done. And people in NASA and all the contractors who worked on it, and all these many hundreds of thousands of people, from the women who sewed the spacesuits by hand to the people with slide rules designing the rockets, we basically said, hold my beer. And here we go. We're going to do this. We've been challenged and we're going to do it. Now you might say, oh, but the motives weren't purely, they weren't remotely exploration. It was all about military and political goals, and it was a demonstration of American technological and might and power and innovation. And somehow the accomplishment outgrew the teeny tiny political military goals of the people who agreed to support it. You go back and look at how many politicians said, this is ridiculous, it's a waste of money. And no government agency has paid the American taxpayer back return on investment like NASA. It's been spectacular. Industrial, medical, materials technology, computer technology, tracking, satellites. It's transformed our lives. We would not have smartphones except for Apollo. The miniaturization, it's just stunning. Well, this week, 50 years after Gene Cernan said, I'm setting the last footprints on the moon for a while. And, the other timeline for me, Scott, 7 years to the day from Apollo 11 to Viking lander.
Wow.
7 years to the day. So when I think of, we haven't been to the moon in 50 years, I'm like, yeah, you guys got better game than that.
Yeah. Well, that's for sure.
We have better game.
It wasn't because we couldn't have done it,
Correct.
Right.
It's because politically we don't have the will, and we don't, as we did then, one of the things we did right is we set hearts afire for space exploration.
Yeah.
And we didn't enthuse the American public. Wow, what a military accomplishment. If we can put a rocket on the moon, we can put a nuke on the moon, we can launch nukes from the moon, and we can dominate the world. Nobody did that. Nobody said that. There were maybe military junkies who were saying that, but in fact, NASA didn't say that.
No.
NASA set hearts afire for space exploration, the grand adventure, the heroes, the ticker tape parade. And some people might say, oh, we overinflated the accomplishment of these guys who rode the rockets. I don't personally think so, but I understand that point of view. But we were setting hearts afire for this. And by the time we launched Apollo 11, half the world was tuned in and watching? More than half the world was tuned in and watching? Apollo 13, billions and billions of people were watching? Well, we've done some interesting things with the samples they brought back this week. For the first time, we've successfully grown plants in lunar soil that is regolith. Let me back up a bit here. We say lunar soil. We think of soil on Earth as something that we find in our backyard, right? We run a tiller over it, we plant corn in it.
Yeah.
We get out with the little crank seed broadcaster and we reseed our lawns. And we think dirt, we dig in it to find worms to go fishing. Soil on Earth is nothing like the term soil. I use regolith because on the moon, soil the term makes no sense. On Earth, soil, yes, it's broken down rocks, but it's also organic material. It's decayed and composted plant material, animal material. It's full of fungi, bacteria, algae, nematodes, insects, burrowing mammals, all kinds of animals, ants, cicadas, all these sorts of animals that dig in and live in, eat in, go to the bathroom in, and die in the soil. The constant churning of nutrients, and the plants absorb sunlight. They convert that to biomaterials, and that decays and it forms the nutrient base. Every year we see the leaves fall. Yay, the leaves are turning color. But these leaves also bring potassium, nitrogen, minerals, all sorts of things back to the soil. Then they decay in the plant matter and the mulch, and they help hold the water. And it's such a complex subject. You can go get a PhD in soil science and be very, very busy. Thank you very much. Learning new and exciting things about the dirt underneath our feet. The moon doesn't have soil, Scott. It has volcanic rock and metamorphic rock that melted when the moon was formed, and the surface has been irradiated and pounded.
No
water,
organics in it, or
no organics, no decay,
no fertilizer,
no decaying plant or animal materials, no insects, algae.
Yeah.
And all of these living things live together in symbiosis. If you take soil from your garden and you put it in your oven at 400 degrees for a couple of hours, and then after thoroughly burning the crap out of it, you go and try to grow plants in it, you find that, you've killed all the little active biological components, and plants don't do nearly as well. They don't do as well. They don't uptake the minerals. There's this symbiosis between bacteria, fungi, algae, and the roots of plants that aid in water transportation, mineral, and all sorts of things. And on the moon, you have years.
Do we have a freeze?
And that's about it.
Say that one more time. You froze up there, Dan.
So they went and they gave them, scientists who did this said, we've been trying for years to get our hands on some actual lunar regolith. They gave them about 12 grams of material. If you think about 12 grams of lunar regolith, that's a very small sample. They had very small micro things they would normally do for growing cells in a bacteriology lab. And they were very teeny tiny cups, less than a cubic centimeter of soil. And they were using a plant related to mustard. That's a common standard plant because we know all of its genetics. And they were planting them and putting some nutrients in their nutrient solution and saying, will this soil support growth? And in fact, to everyone's surprise, it did. Now, the plants compared to a control group, they planted seeds in volcanic ash. And you're like, that doesn't sound like a very tasty soil mixture either. But the plants in good old Earth volcanic ash did quite nicely. Thank you very much.
Oh, yeah.
And we should think about that because volcanic mountains and islands are often some of the most amazingly fertile, biodiverse areas on our planet.
Arenal, it's like emerald green,
Exactly. And this is all over the world. Well, okay. So they found that, these plants struggled. And when they analyzed them, they said, the soil is full of heavy minerals. The other thing that they found is that, the soil that had been more sheltered did better than soil from the Maria, where it had just been pounded with sunlight for millennia. And so they found, wow, there were some differences in where they got the soil, but they realized that, yes, wow, look, we could legitimately have a colony on the moon where people farmed. And obviously, if you're starting out, everything that was not edible would be composted, right? And you would be building soil. Soil would be some of the most valuable commodity in a lunar colony. You know, there's no, who can I sell my recycling to? Nobody wants it. Oh no. In something like a lunar or a Martian colony, this would be one of the most valuable commodities. So it'll be interesting to see where that goes. But 50 years we've been waiting. Gee, can you grow plants in lunar soil, regolith? And the answer is yes, you can. The other one that came up across my search, and I saw this headline and I was like, nah, this isn't true. Cleaner air leads to more hurricanes.
Darn it.
I know. And I'm like, wow, talk about the law of unintended consequences.
Now, Dan,
But
I will tell you, I had a conversation, one of the guys I have conversations with from time to time, retired JPL scientist,
Right.
worked on Galileo, worked on Cassini. I was getting kind of depressed over the, how much pollution we're throwing up in the air and all the rest of it. And he said, it is horrible and it is killing people. Air pollution is killing people. However, he said that the pollution, there are studies where the pollution in our atmosphere have kept things stable. So, it's interesting that as we have gone towards trying to have a cleaner environment.
And we have a lot cleaner air in the United States and
just
Europe
go to
now than we
LA
did
from
50
the
years ago.
1970s when I graduated.
Oh my gosh, yes.
To now, and yeah, the air's a lot cleaner. You can actually see through it now. Not that every pollutant is
No, every pollutant is not.
But,
and we have,
it is cleaner. It is
Right.
cleaner. So,
and to some extent, it's cleaner because we've moved our manufacturing overseas. But that's another.
yes,
we need lots
I've
more
also
beer and
got that
pretzels
experience too. I've
for
seen
that conversation.
The disaster that has.
But
has
it
happened.
turns out that a lot of industrial aerosols cool the atmosphere. And we should know this works this way because it works this way when stars form. Dust, particulate, it's not exactly an aerosol, but it's an analog. Dust particulates in the nebula where a protostar is forming help in the transition between protostar to star because the aerosols, the dust particulates in the nebula, cool the cloud. They have a huge surface area, and so they can absorb light energy in all spectrums and then radiate it away very efficiently in IR. So they allow the nebula to cool, which allows it to compact, which means the core gets hotter, and bang, nuclear ignition. Here on Earth, what we're seeing, aerosols that we had so much problem with in the 70s and 80s and into the 90s, they were cooling our atmosphere over our oceans. And so, what we found in the 70s and 80s, that this cooler atmosphere was repressing hurricanes and repressing hurricane formation. We weren't getting as many. And you go, how can you be sure that's true? Because if you take a look at hurricanes in the Pacific, which we call typhoons, well, the industrial capacity of China and Asia in general, India, has been seriously ramping up since the 80s. And so the Pacific has lots more aerosols over it than it used to. That atmosphere is cooling, and the typhoon production in the Pacific has been falling over the last 30 years while The particulate levels have fallen over the Atlantic and the hurricane production has increased. So is it really global warming making more hurricanes, or is it the clean air people making more hurricanes? Climate is a very, very complex thing.
Yeah.
So I will not.
I will offer one more. Is climate change normal and has been happening all the time?
Sorry?
I said, is climate change normal and it has been happening all the time?
Yeah, I'm missing a bit, but let's just go ahead and move along.
Okay.
Anyway, sorry, your signal dropped out, and I don't know if that's me or you. Anyway, let's talk about Mars, inside and out. And I was going to do, as I was mentioning to you before the show, I was going to do a bunch of little Mars news things and kind of have Mars news today. But I found two things which were so fascinating. I'm like, oh no, these are really interesting. So let's take a look at them. And I'm going to go ahead and show everybody this lovely view here. And there we are. Are we all seeing this? I hope we are. We've got this lovely, and it looks like this horsetail, and it's quite beautiful. And we see it starts up here and then it runs down, and it's like, wow, what is this? It's actually an avalanche. Now, interestingly, the more recent articles on this are saying dust avalanche. Dust avalanche. And the explanation, the current 2020 plus era explanation, is that we have underlying soils on Mars. And again, I'm going to use the term soil advisedly here, but we have underlying soils on Mars which tend to be volcanic, and they tend to be large particles, and they tend to be very dark in color. This image, you might think that, oh, this black stuff had flown down the mountain and flown over the landscape. That's not true, and that's not what happened. The black stuff was underneath. The dark colored material was underneath, and it was covered over with this light layer of dust. And so the dust gets transported by global dust storms on Mars. It's constantly falling. We call it fines because this stuff, what we call dust on Mars, very, very, very fine particle size. The atmosphere is very thin, so stuff doesn't get into the air until it's very fine indeed. And this stuff accumulates over Mars seasonally. And what the current 2020 plus era explanation is that, oh, the dust layer builds up, and the dust layer indeed has a low coefficient of friction. And so it builds up, and finally the weight is too great and it slides down the slope. And so when it slides down the slope, it uncovers these dark subsoils, which in itself sounds really cool and really neat. And these interesting areas, these things were first photographed by the Viking orbiter. So we've been seeing these things since 1976. And so the idea is that you have two kinds of surface material, one which is large grain and has a large coefficient of friction, and one which is extremely fine grain size and is powdery, and it flows almost like a liquid. And we've seen this sort of thing where you get dust avalanches. And dust, in certain situations, it starts to move down a slope and it gets some air mixing in, so the grains separate, and this stuff flows just like a liquid. It's a marvelous, completely non-aqueous analog for a liquid. And so you get this dust that's uncovering the materials below. And you go, okay, that sounds like a pretty interesting hypothesis. And we know for a fact that dust on Mars is always falling out of the atmosphere onto the surface, much like it does here. We struggle with it in our homes, and we're constantly going, ew, this place is dusty. When's the last time I dusted this? And this dust, they say, ooh, it avalanches routinely down hillsides. It's not explicitly stated, but the implied implication here is that, oh, when you get enough mass, the mass and the force down is greater than the force of friction holding the dust in place, and so it gives way and you get a dry slide. However, you go back and you look at some investigations of these slides that have been done before 2010. And the last paper I read was dated about 2004, 2005, somewhere in there. And they note that these streaks occur in areas of low thermal inertia. Well, what does that mean? Low thermal inertia, we're talking about something that heats and cools very easily. If you want to understand thermal inertia at home, friends, you can do it real easily with a frying pan and a liter of water. Go ahead and take your frying pan, cold, set it on your stove, put your hand right on the bottom of the frying pan and turn the burner on and start a stopwatch. How long can you hold your hand there before you go, ow, that's too hot, and you have to take it away? It's not very many seconds. It's not very many seconds. You're going to be able to hold it for a few seconds and you're going to go, wow, I have to stop this. Try it again. Cold frying pan, put a liter of water in, put your hand in so it just touches the water surface and not the surface of the pan. Turn the heat on again and start your stopwatch. You'll find that you can hold your hand on the surface of that water probably more than a minute. Anybody who does this at home, I'd love to see your data. But you can hold this, you can hold your hand on the surface of the water for quite some time. Why? The metal has a low thermal inertia. We say it has a low heat capacity. A small amount of heat creates a relatively large temperature change. Water has an extremely high thermal inertia. It is, in fact, the area that it's a natural material. There's almost no other material in nature that has such a high heat capacity. And so water can absorb a great deal of heat, and there's a great deal of heat, and its temperature change is very, very small. And that's why we use water for cooking. Why? Because when water gets hot, it contains a huge amount of heat, which makes cooking potatoes, rice, vegetables, beans very, very efficient. Well, they said this occurs in areas where you have a low thermal inertia. The surface material warms up very quickly as soon as it gets any kind of solar radiation. Think of sand on the beach, right? We go to the beach, we go, ooh, the water looks delightful. And an awful lot of people, you see these images on the movies all the time of people barefooted running down to the beach. And a lot of us are like, you know what? At noon or 1 or 2 in the afternoon, I'm not doing that. Why? Because we know that dry sand is hot enough to cook eggs. It has a low really thermal inertia. That silicon sand heats up amazingly hot. But as soon as we get to where any of the sand is damp at all, it's no problem. It feels great. It's easy to walk on. What's the difference? The water in between the sand grains is absorbing the heat, and it has this high thermal inertia. So they said, oh, materials on the surface have a low thermal inertia. So we realized that, ooh, these thermal materials are absorbing heat from the sunlight, and they are warming quickly. Well, what's going on underneath that? What are they transferring the heat to? Well, Mars' atmosphere is not a very good conductor of heat. It's almost a vacuum. Hey, You know why my drink is cold? Because I'm using a stainless steel vacuum flask. Oh, vacuum is a great insulator. Hello, Dewar flask. Hello, thermos bottle. Hello, Stanley coffee thermos. Yes, vacuum is a great insulator. So that heat that gets transferred from visible light and infrared and UV, and it strikes the dusty soils of Mars, and it heats up very quickly. That heat doesn't radiate both up and down equally. It radiates mostly into the interior. Well, then they did a little more research and they said, oh, these streaks occur when the surface temperature exceeds 275 kelvins. And I'm like, I know that number. I remember that from chemistry class. I looked it up. Yes, 35.3 Fahrenheit or 1.9 Celsius. Oh, so it gets hot enough to melt ice. Is the ice going to sublimate directly? Not underneath the sand, or the dust layer forms both a vapor barrier and a pressure to keep that, allow that water to transition to a liquid state. And they said, oh, we also noticed these slope streaks form on south-facing slopes. And if we look photographically at changes inside on Mars' surface, we realize, ooh, you know what? If there's an interval and we see a picture here and then it changes here, the only time we see a change is when there's a warm seasonal interval in between. In other words, these sand streaks almost universally occur after the ground heats up, after the ground temperature exceeds 0 Celsius, 32 Fahrenheit, and you're like, is this a coincidence? We also know ice binds things. Ice locks things together, right? Have you ever dug something out of your freezer and stuff is frozen around it and it's all locked in by the ice? Yes, of course. And so we're like, oh. And so the earlier data, people were saying, there is water in them there hills. And when it gets warm enough that the water could transition from solid to liquid underground because of absorbed solar radiation, then we get this downflow. People aren't talking about that explanation anymore. I don't know. This idea, south-facing slopes, temperature over 0 Celsius, and you get changes after a warming period. This looks seasonal to me, and it has all the hallmarks of a water-mediated phenomena. Is it really? And people are arguing about these gullies and streaks on Mars today. Will we ever know? I'm sure we will. How are we going to find out? Well, we could have some kind of a fast-moving rover that could land and crouch and wait, and there's a streak. Run up there and grab samples in real time. Are they anhydrous? Are they water-free? Do they show a humidity content? We could send the rover up the slope and try boring in and taking samples. Of course, if it's an area where they tend to have avalanches, I don't know if I want to risk $1 billion rover to go climb up a slope where maybe it's going to have an avalanche. Boots on the ground would work. But this is
wouldn't
just...
an avalanche be equally as dangerous for an astronaut?
It might be, but I think you would have an easier time having an astronaut hike up to the top of the ridge, or to go and take some kind of
evasive action of some sort,
like a lunar rover, and go on up the slope. I think with a human being driving and controlling it, it would be a lot more doable. We have a lot more processing power. God bless the people at NASA and ESA and all those places that design these things. But yeah, people have more processing power. And you've seen, and I've seen, Scott, you remember being out in California. Did you ever go out to Indio and saw these crazy nutballs with the four-wheelers out in the sand dunes?
Oh, yeah, sure.
Yeah, and you see these people, and you're like, wow,
Been
okay.
airborne, right?
I know, right? I know there's people who could do this. It's a new qualification for Martian astronaut, dune buggy pilot. But hey, so that's one interest. That's the outside part. Like, wow, this is really interesting. Data coming in. The other thing we're looking at is the InSight lander, which has been on Mars for quite a while now.
Mhm.
And the InSight lander is starting to see some really big quakes. Now, the InSight lander landed and put probes in the ground, and it notoriously had some troubles with setting up seismometers but it eventually got the probes deeply enough in, and they were saying, oh yeah, okay, microquakes. There's nothing there that's very big. Why are they interested in quakes on Mars? Mars quakes? Sure. Why are we interested in Mars quakes? A quake sends seismic energy waves, not only up to the surface where they make things shake, but they send waves down into the interior. And as we know, as astronomers, Scott, when you have a wave passing through materials, waves are refracted. And the kind of glass that light passes through makes a difference where things focus, how much it's bent, and the interior of any planet contains refractive materials. For waves, these are seismic, they're essentially sound waves. There's differences there, but let's go with the analogy. Sound waves or seismic waves traveling through a planet. And there are certain layers that they bounce off of. They tend to bounce off of liquids. Liquids are reflective to these seismic waves, but some waves penetrate and they're strongly refracted. And so they're like, wow, we've now got, one of the science writers, and I don't know who it was, and I forget one site, Mars has had an MRI.
Yes.
And I'm like, that's a very nice analogy. Most people would understand that. Oh, I've had this like X-ray, right? I've had an MRI. Well, there were 2 Mag 4 quakes recorded in April, and they had a magnitude 5 quake recorded on the 4th of May. So this is, again, bleeding edge science. And I'm sure people are still very, very busy doing the data processing for this and seeing, what does this show us about the interior of Mars? But all of these quakes were originated in Cerberus Fossae. If we go and look at the Tharsis Bulge region, big bulge region on Martian equator, that's where Olympus Mons and the 4 biggest volcanoes in the solar system are located there. We talked before about surface areas and grabens, big faults with ground sinking in this area, similar to what happened at Death Valley. You had the continental crust spreading and it sinks and you get this extraordinarily low area. We've also talked about the Mariner's Valley. That's caused by crust on Mars cooling, contracting, creating this big tectonic fault. It's not a water-carved canyon like the great canyons in the United States, the Grand Canyon, etc. It's not like that. It's a tectonic fault. And if you look going east from the Tharsis Bulge, there's one other big plume, and that's Elysium Mons, another mega volcano. And in between the two is an area called Cerberus Fossae. It's in the Elysium Planitia. And so you have this big area, and the Cerberus Fossae is huge tectonic faults where you've got these areas where crust has been pulled apart because some areas been uplifted, so other parts have stretched. You get these big grabens, these sinking areas, and surprise, that area is tectonically active. People made predictions before InSight. Oh, the biggest quake we might see on Mars is 4.5, maybe 5. But that would be the absolute biggest. What's your chance of seeing the absolute biggest within a decade? pick any decade. Are you going to see the absolute biggest quake on that fault system? Scott, you and I lived in Southern California for decades.
We had a big one there.
Yeah, exactly. The big one. And they're talking about a massive rip quake along the southern San Andreas Fault. And you know what? Every time somebody says the biggest that's possible in this sort of system, nature kind of says, oh yeah, Fukushima you. The Fukushima nuclear plant, folks, not to demean the disaster, but the Fukushima nuclear plant, the engineers said, we'll build this for a magnitude 8. And of course, what happened? They had a magnitude 9 earthquake that destroyed the plant and had a huge tsunami besides. And so, 5 is the very biggest we can expect on Mars. Part of that was an understanding that Mars was geologically pretty much dead. The era of quakes, the era of volcanoes, the era of all sorts of geological tectonic activities is pretty much done on Mars. Doesn't look like that's exactly true. This area, Cerberus Fossae, which lies between the two largest upthrust areas caused by magma on Mars, is where they're having these big quakes. And so these seismic waves, people are now saying, and I'll share another lovely picture with everybody. People are now saying, oh yeah, Mars has a liquid core. Wow. Mars has a liquid core. And of course, we know, we say we know, Earth has a strong magnetic field because we have a liquid iron core that continuously rotates and uses the magneto effect and generates a magnetic field. Well, if Mars has a liquid core, why doesn't it have a magnetic field? Its rotational period is virtually the same as Earth, 24 hours, 30 some minutes, where Earth is 24 hours. So the two planets are rotating at the same speed. And maybe it's that the Martian liquid layer is all rock. Maybe it's, there's no metal in that liquid area. Don't know. But wow, this is fascinating stuff. And so we talk about these things and we say, oh, gee, haven't we exhausted Mars as a thing until we get there with boots and people? Well, no, we haven't. And
we haven't learned everything about our own planet yet.
No, we have not. And there have been any number of periods in history where very smart people did the same very dumb thing. And they said, science is finished now. I think it was von Helmholtz in Germany in the 1880s and basically proclaimed that physics is over. And all future physicists are going to do is adjust the decimal places on the known concepts and constants of nature because physics is done. And then a couple years later, we discovered radioactivity. And I'm trying to think of the fellow's name. Henri, it's not Poincaré, maybe it is. But the guy who discovered radioactivity, and then the Curies, and the discovery of all the radioactive elements. And gee, what's happening? We look at pitchblende and all those new elements discovered because we're looking at radioactive decay series. And every time somebody said, oh, the science is finished. And we've heard that. And it's a gosh awful foolish thing that occurs. And you see it, we're not immune from it in the 21st century. The client Simon is settled. And true, those were more political than scientific people. But we saw that article last week, Scott. Gee, we should, NASA has a mission to make sure we steer people into the right interpretation of data.
Yeah.
That's pretty much that's a song on the same thing. The science is finished, right? The science is over. No, it's not. The science is never over. There's always, there's always something fun under a rock. And gosh, so I'm just excited by all of this. That new stuff is coming out of Mars, and lots of new things, and I'm just really, really thrilled.
Yeah.
Um,
I think some of the stuff, by taking a fresh look, at another planet with whole new, daunting challenges to do that,
yes,
will probably allow us to look at our own planet in a deeper,
certainly,
more relevant
absolutely
way,
so.
So.
Absolutely so. They're talking about the Psyche Mission, which I'm going to talk about next week.
Mm-hmm.
But I'll give everybody a teaser. And people say, well, why do we want to send an asteroid? Why do we want to send a rocket to Psyche, which, by the way, friends, is a large metallic asteroid? And there's the cynical reasons. Oh, if it's mostly iron and nickel, it's worth like $6 trillion because there's so much metal there. Ooh, that could be a reason. Asteroid mining. But we have other things. We hope that this asteroid out in between Mars and Jupiter can tell us about what's underneath our feet. And so it's going to be exciting. And Psyche is supposed to launch in August of 22. It's going to get there sometime around 2025. And who knows how long it takes for the data to get back. It's not supposed to be a sample return mission. So it's going to be sending data back digitally. So we should find out cool stuff sooner. And if you go look up image of Psyche, you see this artist rendition of it. We don't really know what it looks like yet. But we're going to talk about Psyche next week and how looking out can help us understand what we see when we look in. Because when we look inside the Earth, there's always the question, how do we interpret this data? And we've talked about this on the show many times. How we interpret data, we bring our own cognitive ideas, our filters, our biases, our prejudices, and we say, oh, I'm going to interpret it this way because I understand the world this way. Someone new comes along and says, oh, you're an old-fashioned gink, aren't you? Gee whiz, I have a newer understanding. I'm going to interpret this in a new way. Who's right? Nature decides. An experiment is a question we ask nature, and good scientists are humble before the data. But even if the interpretation is ambiguous now, the steamroller of science will continue and the truth will be revealed. But there's always something more to learn.
That's right. That's right. Well, let's see if we have any questions for you here.
Please. I always love the Q&A.
Yes. There was a question, I don't know much about it, maybe you know more, about light or lightning emanating from earthquakes. Have you ever heard of such a thing?
I don't know much about lightning and earthquakes. I know you can use electrical signals, and pending earthquakes, there's some indication that we may be able to predict them very short term because we see the rocks are stressed and they give off a certain piezoelectric electrical signal. But I don't know, I know there's an absolute and exciting connection between volcanic events and lightning. The clouds of ash material, and they go up and they super cool and they get hail, and the ash and the ice mix and create spectacular. If you go do a search engine, go do a search for volcanic lightning and get some of the images. Volcanic lightning image. It's just stunning. It makes me so much want to go visit Stromboli, Mount Etna. Wow, look at the volcano. Let's watch for the lightning. I'm not quite there with the people who wanted to ride a titanium canoe down a lava flow in Hawaii, but I'm close.
You're close, huh?
Yeah, there's somebody who actually wanted to do that. I'm like, no, but I'll watch the video.
For a one-way trip to Mars, that's for sure.
Yeah, I'd rather have a one-way trip to Mars, thanks, than a canoe trip down a lava flow in Hawaii.
So volcano. Well, from the little bit that I did see about earthquake lightning or earthquake light has to do with the fact, or not. I don't know if it's a fact or not, but the explanation is that there's a electric current inside of some rocks. Okay, and that gets released.
Certainly, piezoelectricity, where we stress crystals like quartz crystals, it's the same reason quartz crystals vibrate when we put an electric current on them and we use them for clocks. Well, if we stress them, we get electricity. If you have one of these barbecue lighters where you have the long thing and the butane, and you click it and you're seeing a spark, what's that? You're actually putting a stress on a little crystal, and it makes enough voltage to get a spark. Could you get lightning from that? I suppose. But it's already in the ground. I would think it would be conducted through the earth rather than, because most earthquakes are, what, 10, 20 miles deep? I don't think you're going to get the voltage channel to go through that much rock. Like I said, I've heard of electric signals predicting earthquakes, and that's kind of cutting edge technology, but I have not heard, and I'm skeptical that you could get, okay, you get lightning go through the air.
Yeah.
Right? And you talk about increasing the potential until you get the spark to jump. Well, you get it to jump through 5 kilometers of air, cloud to ground, right? 5 to 10 kilometers. Okay. 20 kilometers of rock. I'm very skeptical.
You're skeptical.
Very.
Okay.
I mean, I've done no study on this. It's just what I know from first principle physics and stuff. I'm like, I have a hard time with this, because I know when lightning comes to ground, rock tends to disperse it, because there's all sorts of minerals that are semiconducting with enough voltage. The lightning strikes, and that ground effect, that lightning disperses the electrical energy. And you could see this in photographs. Look at photographs of lightning striking a tree, and you can see there are wonderful photographs where you see the electrical energy draining away 360 degrees into the soil. And so how are you going to accumulate that much charge, translate it up through kilometers of stone without dispersing it, and then have it go up into the atmosphere?
Great.
And
there used to be a guy at the Riverside Telescope Makers Conference that sold pieces of fused silica sand from lightning hitting the ground. Okay?
I know what those are called too, and
yeah, they look like these wild branches and stuff.
Yeah, they look like branching structure where the lightning's going into the sand and fused the silica.
Right. And
there's a particular name for that. I want to say fullerite. There we go.
That is a crazy, I mean, look at all that power.
Yeah. And that's probably something like a 10 to 30 second time lapse. But yeah, volcanic clouds create this huge potential. Any more good questions before we go?
Well, let's see.
Because I love it. Audience, our friends in the audience, I love it when y'all send in questions. It's just loads of fun.
Harold Locke says, also an amateur radio guy notices high-pitched sounds that precede earthquakes.
Yes, and that would be that piezo and radio signal, absolutely. And I think other people have noticed that, Harold, and that's partly what led to the research. Can we put electrical and radio probes in the ground and detect the signals and go, oh, quake on the way? And it's not that quakes don't give these signals. Part of the research is, what's a signal that all quakes give? Or what's a signal that all big quakes give? And the lithosphere is a very diverse environment, whereas the atmosphere really is not. The atmosphere is quite homogeneous in terms of the percent of nitrogen, oxygen, carbon dioxide, argon. The temperature at different layers fluctuates, and yes, we have water, weather rather, but we're talking, relatively speaking, pretty homogeneous environment compared to the lithosphere, which is really, really diverse, which is why we can't just drill anywhere we want and find oil or minerals or metals. The lithosphere is really diverse, and we have to understand it in order to find and extract those, materials that are worthwhile. We can't just dig anywhere and strike oil. We have to have geologists, which are very highly trained and very clever about these things.
Right. There is a member of the audience here that would love to have lunch with you. And Tarek would prefer to have dinner with you. Maybe we'll have a contest where you can win, supper with science with Dr. Daniel Barth.
You are luckier than you know, because I am an excellent cook.
Oh, wow. Okay.
I paid my way in high school cooking for small restaurants, and during college for very big and fancy restaurants for big corporations, and I do all the cooking at home. I am an excellent cook. I have cuisines that I'm better at than others, but yes, it is a well-known thing. Dinner at Doc's is a wonder. And hey, if you all can get to, I'd be happy to have a dinner with Doc contest.
Yeah,
of course, I would not provide you with airfare to get to Northwest Arkansas, but I would pick you up from the airport.
That's right, and I'll give you a free tour of Explore Scientific. So
and we have plenty of space here at the ranch to have guests, so that would be fun.
Wonderful. All right, guys. Well, thank you so much. Hope many of you got to see the eclipse.
Yes.
If you were clouded out, I hope that you watched our program last night. We had a fairly sizable audience watching from around the world. I was really shocked at how much the globe was actually in clouds during this time, but we had people down in Argentina that got it for a while. We got our Marcelo Souza in Brazil was successful in showing it to as an outreach event, so we had a lot of people there.
Some of my friends in California texted me pictures to make me
California
jealous.
was clear. Those lucky son of a guns, yes. People in Nebraska saw it as well because it was very clear. So, but if you were probably anywhere west of the Mississippi, you were having trouble. We had issues here in Arkansas.
We did.
From what I understand, Texas was clear. Or parts of it, anyways. But Texas, someplace in Texas, is always going to be clear because it's so dang big. Anyways, thanks so much for watching today. Tomorrow we will have Global Star Party. It's our 94th Global Star Party, and it is about the theme is transformation. So anyhow, you guys keep looking up, and we will see you. We'll see
next
you soon.
week.
Yeah,
That's right. Bye-bye now.
Billions of years ago, Mars was able to have highly explosive volcanism, and it's not just a one-off, but we had many episodes of highly explosive volcanism in a sort of short geologic window. Two folks found these things that look like impact craters in Arabia Terra, but they're missing some features and they have some different features that actually make them look more like volcanic caldera formed from explosions. On Earth, we can't actually see this far in the past in many places because we have erosion on Earth, so we don't have access to a great geologic record for 3 billion years ago on Earth. On Mars, we can see that. We're trying to understand just how large explosions or large lava flows on places like Earth, but also other planets, might affect the climate. So we know from just the last century very large volcanoes do have a climate impact. This tells us something really important about the history of Mars and in turn the history of just planets in the solar system.